give online.
Do they have any significant advantage trying to give it online? Like the
No, sir,
consultation is easy or something?
not really, sir. No.
How many of you have onboarded?
So
Can
I
you tell
think
me?
there are 6 people.
Out of 75
Yes, sir.
only. Okay, then forget
Yes.
it. Then forget it. All of you give it online. Um,
Yes.
some of your colleagues have this very interesting habit of not even joining online, but actually submitting answer sheets and quizzes. They will please inform them that they will get a 0.
Okay, sir.
If they don't join online and submit the quiz, they are not allowed to submit the quiz or the entrance exam if they have not joined online. And
Okay.
they cannot
So,
say
sir,
I could not join online because I was having some problems. But they have the time to submit the answer sheet.
so sir,
That is clearly unacceptable.
this applies for quiz, or will this apply for minor from now on?
It will apply for everything, for every and any exam. You cannot say I will download the question paper, disappear, and after 1 hour submit the answer sheet
Sir,
without any
because
invigilation.
sir,
Yeah.
because for this quiz the information was given quite late. We didn't know that we had to join a
What do
meeting.
you mean? What are you saying? Deepra, just think
So
what you're saying. You say
there
you will
was a
not be invigilated either online or offline. You will download the exam and then you will do whatever hell you want to, and then you will submit the answer sheet. What are you saying? Just think about what you're
sir, because
saying.
this has been the case in most of the courses for
What
the
people
last
have given exam. Hold
and
on. Let me be very clear. I mean, I think I'm getting agitated. Let us get it clear from you. Are you saying that people take the question paper and disappear and after 1 hour submit the answer sheet without any invigilation whatsoever? Is that what online means? Are you saying this? Because I will then record it and send it to the director and say, this is the opinion of the class representative. Let us have it very clear from
not
you.
my opinion. All I want to say is that Ratnesh and some other people missed because the information was given quite late, and
What did they miss? Exactly what did they miss? Let me know.
Ratnesh
What
said
did they
that
miss?
he didn't know about that they had to join a Teams meeting.
They did not know that they will be invigilated during exam.
Yes,
How
sir.
did they know how to download the question paper from Teams?
Because that information was given like
Okay, so when you join in Teams and
I
download
was
the
just
question paper,
asking
you are
for
supposed to. No, they
I
play.
was just
No,
asking for a
let us
waiver
have. No,
for
what are
this.
you asking for? Just think about. You are saying that I
I
will
said,
download the question paper and disappear. Let us be very clear about this. What are you asking for? Because you give it to me in writing that I will take the question paper and I will disappear to online exam and I will submit it to the head and director. This is what the demand is. Just think
this is not
about
just
the
asking
ridiculousness
a
of the demand. No,
waiver
no,
for
but what are you saying? No, Dave, hold on. You download the question paper in Teams, the exam is being conducted on Teams, and then you will not join. And you will disappear. And you expect after 1 hour to rejoin and go to Moodle and submit the answer sheet. Have you ever given exams without any invigilation whatsoever? Ever?
yes, sir. We have given exams. Yes,
Even in the online mode, even in
yes, sir.
offline mode, can you just send me a list of those exams and I will submit it to the writer that you people are not invigilated when you are given normal end semester and mid semester and quiz exams. You just send me a list of that, please. I would like to
Okay.
submit that document to the head
Please
that
check some
exams
of
are
them
conducted
ready.
without no
If they don't,
invigilation whatsoever, no overseeing of when you are giving the exam. All of you, is that what you're saying? That's
can
very
someone
interesting.
else confirm Ashi Vishantan?
No. You give me the names and the exam list and the days they were conducted when you have had exams where there was no invigilation whatsoever, and whether it is a standard practice in the institute. I mean,
Mm,
you are making a preposterous claim that you will not be invigilated at all. You will say that the right to invigilation is now removed. I will download the question paper. Online means that I will not join. I will not be invigilated during the time that I am good answering the answer question paper. This is a absolutely unacceptable demand.
no, sir. I was only
Every
asking for
time,
this
every
clarity.
time you have given a BTech exam, have you or have you not had invigilation? That is my very simple question.
Not always, sir. No, sir.
Not
I can
always. Give me a
technically
list.
prefer.
Give me a list of the times when you were not invigilated and you were given an exam, regular exam, minor, quiz, etc., where it was not specifically stated that it is a take-home assignment. When it was an examination and there was no invigilation.
So
I would
that was
like
the case
from
of
you a list
CLL
of such
252
people.
and CLL
Sorry?
261 in the minor.
Just send it to me and just send me an email that this was the exam, this was the class teacher, and it was a quiz or a minor or whatever, and there was no invigilation whatsoever. And it was not specifically stated that it is a take-home exam. It was an exam which was supposed to be invigilated. I would sort of like to bring it to the notice of the head that this is also a practice which is followed.
Okay, sir. Sir, and now I'll inform everyone that they will be given a 0 if they don't
There is
join
no
the
need
meeting.
to inform. There is no need to inform. Examinations by definition are meant to be invigilated. It is a de facto rule. Is it that you have a de facto rule that you will not attend unless you are told? That you will come and collect the question paper and answer sheet from an examination hall and go away, run away and come back after 2 hours and say, here is my submission? Do you do that in the offline mode?
No,
Or you
sir.
come to the examination hall? Do you come to the examination hall, collect the question paper and say, thank you, I will come back after 2 hours and submit it? Is this the de facto rule or is it sitting in the examination hall the de facto rule?
This sitting in the examination hall is the de
So
facto.
then why should the same rule not apply online? Why do you have to inform everybody that we have to sit there? No, I mean you are creating it is like saying कि कहाँ लिखा हुआ है कि गंगू तेली नहीं आ सकता है क्लासरूम में बैठने के लिए कहीं लिखा नहीं हुआ है. I mean you cannot generate such things कि what if this is not written? There are de facto rules. I will not announce everything. Sorry, that's not my job. You're supposed to know that an examination has to be written and attended. You cannot run away with the examination paper and say I will submit whenever I want to, because it is not written. I mean, there has to be some basic principles here. Think about it. I mean, you're coming up with preposterous suggestions that, I will now inform that they have to actually sit in the examination. They earlier thought they can disappear in the examination. Just write this out and write to the head that we do not know that we have to sit in exams in the online mode. We thought we could download the question paper and disappear. Please write to the head. He will give you a very nice reply. Far nicer than me. Okay. Anyway, let me not get too worried about these claims. I mean, I have never seen such ones, but I would also suggest that you please go to your class notes and download the 2 books that I have given, because I've managed to look at Herbert Saro book, the book which is important. The first 3 chapters of the book will be the part of the minor exam. So let me sort of minimize this.
Sir, what will be the
sorry?
Sir, what will be the syllabus for the minor?
Till whatever has been taught till now, till today.
Okay, sir. Okay.
So, which essentially is recombinant protein production.
Sir,
The whole method. Sorry.
Sir, the course is in D slot and D slot is mentioned on 16 February. It is not on Tuesday.
It is C slot. The course is in C slot.
But sir, at academics it is showing that
We are teaching, the timetable is C, isn't it?
No, sir, for all of us it's showing D slot.
D slot, sir.
How come? Because I thought we are teaching 9 to Tuesdays, Wednesdays and Fridays, 9 to 10. What is the timetable that you have?
So it
Sir,
is a
at
9 to for Tuesday, Wednesday, Friday, but the course slot is D slot as per e-academics.
yes, sir.
The course slot is D slot.
Yes, sir.
Yes,
But
sir.
the timetable is C slot. Is what you're saying?
No, sir, it is also D slot. I think. Let me check.
Please do that. Go ahead. We have classes in the C slot.
No, sir, I just checked. 9 to 10 is D slot on Tuesday, Wednesday, Friday.
Is D slot?
Yes, sir. So C slot is 8 to 9.
Okay, so D slot. Okay, so D is what? What date is D? So I'm making a mistake now. What date is D?
16, sir.
Sir, it is 16th February, sir. Wednesday,
Wednesday.
and end time is 10 a.m.
16th is Wednesday.
Yes, sir.
So let me write it here so that everybody knows. D slot, and I thought it is 8 to 9, but it's not 8 to 9. You're right. D slot and 16th, right?
Yes, sir.
Midsem exam.
End time
16th.
is right. Yeah.
16th is what? 16th is Wednesday,
Yes, sir. Yes.
and end time is
10 a.m.
So
10 a.m.
Yes, sir.
Yes.
So let us start at 8:30. Okay, to 9:30,
Yeah, with 10 minutes. Yeah. Yes, sir.
and then 9:40 you submit.
Yes, sir.
A cutoff time. Is this all right with all of you?
Yes, sir.
16th, 8:30 to 9:30, and 1 hour, 20 marks. Online. All of it is online. On Teams.
and so the format would be the same as the quiz, right?
What exactly do you mean by format?
So like two to four questions, and then we just have to write the answer and scan and submit.
Absolutely. You whatever questions I give you for 1 hour, maybe 1, 2, 3, 4, whatever, and then you solve it or write about it, take pictures and submit on Moodle.
Fine, sir.
Okay. Oh, thank you.
Yes.
So now
Sir,
let us sort of, yeah. Any questions?
sir, about the yes, sir. Sir, in the BBL 433 lab section, you also mentioned there is going to be a minor.
Let me think about it, because then I have to hold the minor for your senior batches also. So this minor, the lab minor will not be in. It will be in the lab timing. I will announce it as per. Okay. Yeah, so that is an independent thing. Let us forget the lab, because there are two sets of students working in that, so I have to coordinate it a little bit. Okay.
Yes.
So is this all right? All of you can see this, right? So right
Yes.
now, what were we? Where were we? We were essentially saying reversible enzyme kinetics, right? And so that's. I hope it is simple enough for all of you. So. Where were we? So essentially, we were saying that okay. So essentially, we were saying that to sort of revise, V is equal to Vf minus Vr is equal to, and I hope you. I mean, of course, originally it was this actually V. अरे भाई मेरे क्या कर रहे हैं? Which is, and this was, what was VF? Can you tell me quickly? VF was VF max S upon KS 1 plus S upon KS plus P plus P by KP. And similarly, V reverse was V reverse max P upon KP 1 plus. What is this today? Started giving trouble right in the beginning. Oh. Can all of you hear me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah, and can you see the screen?
Yes, sir.
Yes, sir.
So sorry, I pressed the delete button twice and that's what happened. I mean the power button twice, S plus KS plus P by KP. And what I did was I used the Haldane relationship of VFSS. So I hope you are all sort of familiar with this. VFSS upon KS is equal to VR. Of course, this is equilibrium. VR P upon KP. Equilibrium relation values. To and use the concept definition of rho as P upon S upon P equilibrium upon S equilibrium. To get what? Can you tell me what was the V? V is equal to VF, right? VF max, remember, which is just the maximum velocity, 1 minus rho into S upon Ks, 1 plus S
Whether
upon
with the
Ks.
yeah, plus P by K.
So essentially you have so why I'm writing it like this is that this is the maximum velocity forward, maximum velocity. This is the thermodynamic term, how far it is from, this is the thermo term, right? And this is nothing but the fractional saturation. I'm trying to sort of get it down exactly to the level that I was trying to get it down. So this is the fractional saturation, this is the maximum velocity, this is the thermodynamic term. All of you follow this argument? Right?
Yes, sir.
Yes, sir.
And so, and I also pointed out that the total saturation was, was, I'm not going to write it again and again, I'm getting bored now. This one and this one. And as I pointed out that the total saturation, you do not get it guaranteed. You do not get a saturation when just simply S greater than Ks does not guarantee total saturation because P also has to be greater than Kp. So the total saturation was this, and I developed all the various relationships that basically the saturation values are nothing but V by Vf. This is also V by Vf, and this saturation is V by Vr. Right? VR by VR, sorry. I mean Vf by Vf max and V reverse by V reverse max are the saturation concentrations exactly like it. So I hope you can see that this is the equivalence with monod kinetics. Now exactly in the same way, what is the elasticity? What about the elasticity? What is elasticity of V by S? इसका तो कुछ नहीं होगा, इसका तो 1 होगा. 3 terms here, 1 and 1 minus rho. Remember what was the elasticity? Forward reaction V by S. All of you remember? Hello? Forgotten? I'm waiting. So this into, I mean, this is just constant, so we can ignore this. What is the 1 minus rho elasticity? 1 upon 1 minus rho. Remember? You're missing out, forgetting all the things that we did earlier. 1 upon 1 minus rho. And this, remember I talked about, and so this is U into V form. And so what would this be? Minus S upon Ks, fractional saturation. So I derived the same equation for upon 1 plus S plus K. You follow this or not? I mean, you people told me to move fast, so I thought I'm not going to sit and derive this now. Then. Because remember that elasticity for monod kinetics, what was elasticity for simple monod kinetics? Km upon Km plus S.
Plus S.
Which was 1 minus fractional saturation. The same way, so this minus this. So this is how you get. So the elasticity V by S is 1 upon 1 minus rho minus S upon Ks. This is the fractional saturation. This minus this. Now it is not 1 minus this. It is 1 upon 1 minus rho because now you have the thermodynamic term as well. Because of reverse kinetics. So it's a combination of the mass action kinetics principle and the principle for monod kinetics. Right? So you can sit and sort of, you can write the UBY form and do the partial derivatives and find out the elasticity. D of ln B by D. So I'm sort of going to jump over this derivations now, which is simple algebra. Okay, I'm just trying to say that this is the thermodynamic equivalent which we derived from our mass action kinetics. This is 1 minus fractional saturation logic which we derived from our monod kinetics. And so, in an analogous fashion, can you tell me what is the reverse? What is the elasticity for the reverse? What is E V by P? क्या होगा? I hope you remember minus rho upon 1 minus rho. Remember this term
Yes,
here, this term here, and this term here added up to 1. The thermodynamic rho upon 1 minus rho, and again minus, now the fractional saturation again, P by Kp upon 1 plus S by Ks plus P by Kp. So that same argument. So you can see that there are two saturations here, one EV by S term here and one EV by P term here. Very, very similar and analogous to the monod kinetics and the mass action kinetics. And I hope now you can see what I'm trying to prove here. I mean, other than of course the more. So first of all, what is the EVB, for example, EV by S plus EV by P? What are the sum of elasticities? What about the thermodynamic sum? That by definition the thermodynamic sum is 1. Right? And this is minus this plus this. So remember, so it is S by Ks plus, sorry, Ks plus P by Kp upon 1 plus S by Kp, Ks plus P by Kp. Okay? All of you with me till now?
yes, sir.
So what do we get now? This can be simplified easily enough. So it's just nothing but 1 upon 1 plus S by Ks plus P by Kp. Right? So you can see that we have two extreme situations. For example, let us take the situation where, for example, low saturation. What is low saturation? Very, very low values of, so low saturation is when S is very small compared to Ks and P is very small compared to Kp, right? Low saturation. The system is not saturated. Okay, low saturation. Very low concentrations of substrate enzyme. Something which happens in the cell, inside the cell. So what is it? When there is low saturation, what do we have? Then, of course, this term here is equal to 1, right? Because these are low values, then we can say that EV by S plus EV by P is equal to 1. So they are therefore inversely related to each other. And therefore, if any the response of the velocity with respect to change in substrate concentration is exactly equal to the response of velocity with change of product concentration in the opposite direction when systems are at low saturations. Okay, and more commonly in actual industrial usage, we have high saturation. Right? So what happens when it is high saturation? Then of course these terms are very large. So 1 upon this plus this term here is actually going to 0. So EV by S plus EV by P is actually approximately 0. Okay? And so EV by S so you understand that EV by S is actually equal, no, sorry, this is, I'm so sorry, this is actually true for this one. And for this, it is 1 minus this. So for high saturation, it is this. So can you now sort of let us? I think we are doing too much algebra without actually solving problems. Can you now solve problems? For example, let us take the situation. Let us do a simple problem, and then I'll get an idea of whether you have understood or not. Let us take a simple situation: a substrate going to product, and I say that the equilibrium constant K equilibrium is equal to, say, whatever. Let us say 3 or 2, and P is, let us say P is equal to let us say 2.1, and let us say S is equal to 4 at this concentration. What is EV by S? And let us say V forward and V forward max, and V forward max you don't need, right? V forward, you really need Km and Kp, right? Ks and Kp. Let us say Ks is 2 millimolar and Kp is say whatever, let us say 1 millimolar. Can you tell me what is this elasticity at this values and equilibrium values at this? So what is EV by S? Hello, yeah, 1 minus rho. Is it 1 minus rho? Or 1 upon 1 minus rho?
So 1 upon 1.
Minus S upon Ks. Right? Okay. So what is 1 upon 1 minus rho? That much you can tell me. What is rho? What is the value of rho?
So gamma by KEQ.
So gamma, what is gamma?
P by S by KEQ. So 2.1 by 4 by KEQ.
Yeah. Now let us suppose I had this as, let me say that this was the case. So it's 4 upon 2.1 divided by 2. So how much is that?
Two by 2.1.
So no, I want this term here. What is this term here? Somebody has a calculator. I think some of you should. You people
8
keep
by
on saying we don't get
5.9.
questions. Sorry?
8 divided by 5.9.
This term here.
Oh, yes, sir. 1 upon 1 minus rho.
Bit odd. What is 4 upon 2.1?
Just a second, sir.
0.95. So like
So
0.9.
shouldn't it be 2.1 by 4 divided by 2?
This is what? Okay, let us do it slowly. Let us get back to class 10th. What is P? What is the value of gamma?
So 1 by 1 minus rho is 21 approximately. 1 by 1 minus rho is 21.
Approximately. Good. And what is the EV by P, which is minus rho upon 1 minus rho?
Approximately 19.95.
अरे भाई, this plus this is 1, तो इतना तो भाई minus 20 तो बोलो. If you say this is 20, then please say this is minus 20. At least do such obvious rounding of errors. Okay, this plus this is, I have shown that this is 1 minus rho plus this is 1, right? I hope you remember your derivations. Now notice that this term here is always less than 1. So any 21 plus minus some number less than 1. Some number less than 1. Right? So it is approximately 21. So very close to equilibrium. with a K equilibrium rate of 2 and P equal to 4 and S equal to 2.1, it is approaching equilibrium. So mass action kinetics is dominating, the thermodynamic term is dominating here. This term is negligible, can be safely ignored. I don't need to know Ks and Kp, etc., etc. And to find out. So at close to equilibrium, the dominant force is 1 upon 1 minus rho, and the dominant force is minus rho upon 1 minus rho, because the denominator 1 minus rho is becoming close to 0. As rho approaches 1, because gamma and K equilibrium become equal, as rho is gamma upon K equilibrium, and obviously as gamma is approaching K equilibrium, rho is approaching 1, 1 minus rho is approaching 0. This term, the elasticity is going to go to infinity. That is what I showed in your mass action kinetics, right? I showed that in the mass action kinetics. So the contribution of the saturation terms becomes negligible. So the important issue really is, and this is what I want you to discover now, because we will not go further than this, I want you to do as your homework, is when these things are far from equilibrium. Close to equilibrium, you can safely ignore these terms, because it is 1 minus rho, and so it is really these terms which dominate, and you don't need to bother, because you can see this is 21 and 20, and S upon K, S upon 1 plus S upon K plus P by Kp, whatever be the values, they will be all they will all by definition be less than 1, right? S upon Ks, the denominator is larger than the numerator. So by definition, the fractional saturation component contributes less than 1. So only when rho values are, let us say, 0.2 or 0.3, in which case 1 upon 1 minus, let us say 0.1, far away from equilibrium. Then obviously this term here, the 1 upon 1 minus rho term here is, 1.1. In which case the fractional term, saturation term becomes important. So the fractional saturation term contributes significantly to the elasticity only for far from equilibrium. Is this argument clear to all of you? Or am I?
So just one question.
Yes.
So sigma would be equal to 2.1 by 4, right? I mean, it's product divided by the substrate.
Yeah.
So sir, the rho value.
Product
The
divided
rho
by substrate.
value should also be 2. Okay. Sorry, sir. I just missed that
I
part.
changed it. That is why I realized my mistake, and that is why I changed it. So वो तो obviously 2.1 upon 4 is far from equilibrium. When I said K equilibrium is 2, I forgot that it should be half. Actually, I forgot. So K equilibrium is 2 means the product will be more, right? P upon, so K equilibrium is P equilibrium upon S equilibrium. So that is it, right? So I wanted to make it 2, so this will be at 4 and 2, they will be close to equilibrium, right? That makes sense. That is why I said 2.1 and 4. I mean, P is 4, and so really the argument is that when it is close far away from equilibrium, these are, then you think about the two conditions that we are talking about. One, where S and P are much higher, this is the industrial condition, than K, S and Kp respectively. That's the industrial situation. And the other, when they are far away from so low saturation and high saturation, when they are far from equilibrium, I want you to see the book and solve the questions. Choose numbers like Ks is 2 millimolar, Kp is 1 millimolar. Choose product concentrations far from equilibrium and substrate concentrations far from equilibrium, which are, let us say, 0.1 millimolar and 0.2 millimolar, something like that, very small amounts. Okay, so their ratio should be far away from equilibrium, and choose these numbers, and so both P is less than Kp and S is much less than Ks, and see what is the kind of sensitivity you get, or EV by S that you get, and otherwise choose concentrations of P and S as 100 millimolar and something like that, which is much higher than Ks and Kp, and then tell me what is the kind of elasticity you get. These are the questions that I want you to go back and solve. Is this clear?
Yes, sir.
This arithmetic exercise you do. Let us do another arithmetic exercise before we end. That's important. I mean, we have forgotten. So now we just now talked about two kinds of reactors. The PFR. Of course, we made it the ideal PFR. I don't want to get into complications right away. Maybe later on if we get time, which we may not because of so many aspects. The ideal PFR is essentially the batch in time, right? batch in time.
Yes, sir.
So really, the integrated Michaelis-Menten kinetics applies to PFR. Integrated monod kinetics. So if I tell you that this thing enters here, and I mean, let me sort of put it in a more practical way. Let me sort of spend some time on this. So essentially, a column usually in industry is packed with beads, and I'm not going to get into. Okay, maybe later on I will talk about the same thing in more complex ways with mass transfer and so on and so forth. But let us now think that this is packed with enzymes. Let us do this simply and let us not do it too fast. And this enzyme has a kinetics called V is equal to V max S upon Ks plus S. Right? Simple monod kinetics. Substrate is entering at S naught, leaving here at some value S, and of course some P out is coming out. P inside, P in is 0, obviously, and P out is some value. Please remember that S plus P is equal to S naught. Okay, so please remember that all the kinetics that we are doing in actual experimental cases where S is going to P, you should be able to solve it by the fact that S naught is equal to S plus P. So your for example, your gamma value is not P upon S, but actually S naught minus S upon S. So there is only one unknown, not two unknowns. I hope you remember that. Sometimes you tend to forget the obvious things. And I'm sort of mentioning this very minor point because this will come in useful when you solve problems. So now, right. So now let us get down to this. And so we have this value. And of course, this is entering. And if you have a certain length, if you have a certain length and a certain velocity, you know the time, L by B, right? The tau. And if you assume that this is the same as the time, so then you can write this equation as ds by dt, V max S upon Ks plus S. And what is the integration of this equation? You know this? So S. So Ks plus S upon S into ds integrated is equal to V max T, right? And this will be integrated from 0 to tau, right? Assuming that this is perfect flux flow and there is no Peclet number involved here. The Peclet number is very large, so there is no diffusion, because remember diffusion will create all kinds of issues here. So let us assume that for the time being there is no diffusion and we have this enzyme kinetics here, and so no external mass transfer, no internal mass transfer, no irritating troubles are there. The simplest case, this can be solved by you people. Yes, this I don't need to solve. Okay.
Yes, sir.
This is obvious, right? Now let us do now tell me what happens when S goes to P in a forward backward fashion. Let us say I am converting glucose to fructose. And I want you to now solve this problem. And I say that let us say K equilibrium is, I have all kinds of problems now. I can think of all kinds of problems which I want you to go back and solve as part of your undone assignment. I have a K equilibrium equal to 1. I say glucose coming in at 1 molar. So you know that at equilibrium it is 0.5 and 0.5. Now I say I want 95% conversion in an industry, which means I want at least the outlet concentration of not more than 55.55 molar. Obviously the fructose concentration outlet becomes 0.45 molar. Now what is the T? What is the tau? What is the tau that you require to convert it? Now this is no longer the simple integration, because now V is not equal to this equation here. So now what is your V? Your V is equal to Vf 1 minus rho S upon Ks upon 1 plus S upon Ks plus P upon Kp. So this is your V, and I can think of two kinds of problems. As I said, one, I can think of a CSTR where this is S naught and this is S and P, where P is equal to S naught minus S, S naught is equal to S plus P, and I have a CSTR and I have a dilution rate F by V, right? And the reaction rate is obviously dependent on both S and P. which is captured by this rho here, which is equal to Vf max 1 minus, right, P upon actual P upon S divided by K equilibrium, right, and this into S upon Ks plus 1 plus S by Ks plus P by Kp. And I have now this P is nothing but S naught minus S. Correct? Because
Yes, sir.
this, so you have only one unknown. If you know everything, if you know all the kinetic constants, and then I know the reaction rate, and then of course I can set up the simple material balance d S naught minus S is equal to reaction. So it's just an algebraic problem, and so at different dilution rates I can I can this is a simple equation, this is a simple algebraic equation, and S is the only unknown. Remember, this P here is also S naught minus S. Hello? Are you following this?
Yes, sir.
Yeah,
Yes,
and some of your friends told me to go a bit faster, and you're right, I have to go a bit faster. We don't want to. This is the algebra that I want you to go back and do. And of course, the other is the other part is and this so another part is if it is a PFR, then of course this is nothing but this equation here. Okay, is also ds by dt. Right, and so I have to bring all these things here, and I can bring, so I have to get on the left hand side, I have to get ds upon ds into, sorry, 1 plus s by ks plus p by kp. Am I doing it right? Yeah. Divided by 1 minus rho into s by ks is equal to vf dt. And from there, we can solve for the time required for doing this. So that is one set of problems, one kind of problems that you have to solve. And P here and rho here, where rho also implicitly contains P here is nothing but S naught minus S. So this is an integration which is easy enough to solve for different values of Ks and Kp. And I would like you to solve it. General case S and Ks and Kp might be slightly irritating to solve. Put some numbers and solve it for yourself and find out how much time is required to get how much conversion. Suppose I say I want 20% conversion or 30% conversion, then you have to also remember what is K equilibrium. And if say K equilibrium is 50-50, then I want 40% conversion is what is the X with respect to K equilibrium. You cannot. What is the maximum theoretical conversion that is determined by K equilibrium. So these are one kind of problems which is essentially what happens when you know the values of the parameters. These are the prediction, the simulation equivalents. And the other set of problems which we also did is estimation of parameters. That I run a CSTR and at different dilution rates, and this is the S out that I get. And from such a data, how do I determine Ks, Kp and K equilibrium? Or if I know K equilibrium, how do I find out Ks, Kp and Vf and Vr? And what do I need to know? What I cannot find out from such an experiment of different values of D and S. And so how do I generate my data? So these are the two opposite kinds of problems that you need to solve. One is estimation of parameters from actual experimental data. This is at this dilution rate, I get this substrate concentration. So if I do a plot of let us say I have glucose going to fructose, which has a K equilibrium of 1. So I know that at dilution rates which are very, very low, let us say 0.1 minute, a minute inverse, and glucose concentration input is, let us say substrate input is say, let's say 100 millimolar. and I know that the saturation constant, the K equilibrium is 1. K equilibrium is 1. So the maximum you can, so, and the outlet substrate concentration here, this is S naught. The outlet at 0.1 is almost close to equilibrium. Let us say only 50 millimolar would be left over. So now let us say that 55 millimolar is left over at 0.1, and at 0.2, 60 millimolar is left over, and at 0.3, 70 is left over, and 0.4, 80 is left over. And then using this data, can you now, given the fact that you know K equilibrium, and let us say if I give you some value of V forward or V reverse, can you find out Ks and Kp? Remember that the Haldane equation, anyway, out of these 5 variables, K equilibrium, Ks, Kp, Vf, V4, these 5 variables, only 4 have to be determined. The 5th one gets determined on its own. So since you know K equilibrium already equal to 1, out of these 4, 2 can be determined and 2 have to be known to you from this experimental data. Let us say I know Vf and Ks. Can you find out Vr and Kp? So I want you to go back and solve these things, these experiments now. Or shall we do it here in the class? We have 5 minutes. Any questions? Think about it. So there are 2 sets of problems that you have generated. One is estimation of parameters from data in experiments for reversible enzyme kinetics. Now earlier it was simple enzyme kinetics, but simple enzyme kinetics is the one which is there in all biochemistry textbooks. What they don't deal with, and this is where engineering comes in, is reversible enzyme kinetics, which is really the subject of interest for most engineering applications. Because if you ever sort of design technologies for industry, the first thing you will be told that if you want to work with enzymes, you have to work with enzymes which are doing transformations, and almost all of these have very low delta G values, and since low delta G values means K equilibrium is around 1, 2, not 1000 and things like that. It's 1, 2, 3, 4, whatever. So let me stop here, pause here for a minute and ask, because we have to end this class, and as I said, Wednesday you have an exam. You want a class for solving problems separately? We can think about that. I can bring in problems, but this is the essential set of problems. I would like you to put numbers like this, like I wrote here, and the reverse. I want this much percentage conversion given these values, and actually derive both situations. What is the performance in a CSTR? What is the performance in a PFR? In an actual industrial setting, the way we do design problems is that we run CSTRs, generate this data, and then predict a PFR performance. You understand? The CSTR is usually used as a, why do you think we don't use the CSTR for such experiments? Any opinions? And why do we prefer a PFR for such experiments? Hello? Somebody there? Yes. Yeah, at least 10 of you, 10, 15 of you are there. So tell me, why do we, I mean, while experimental data checking is always done by CSTRs, I can always pack the column. Why is it that we prefer a PFR, a column for, I mean, we never have it horizontally, we always have it vertically. So sorry for this incorrect drawing. Why do we have it like this? Why do we have to prefer a PFR for any S going to P? I hope the answer is obvious and not a CSTR. Yes, please.
Maybe because the conditions are uniform for like all.
So ये तो अच्छी बात है. So if it is uniform, is it good or a bad thing?
So I would say it's a good thing. Like in a PFR, since all of them enter at the same time and exit at the same time.
So this here condition is different from this condition here. Clearly, right? Is different from this condition here.
Yes, sir.
How is the substrate changing in a PFR? Sorry, CSTR, PFR. Sorry, you're right. PFR. The substrate concentration is here, somewhere here, and it is falling. Right? And the concentration of the product is उल्टा होगा. ठीक है ना? ये P है, ये S है. And obviously it doesn't go to 0 remember this is the line is here. So obviously it's a bad drawing actually. Sorry. So I made a bad drawing. This is substrate. No, sorry, I should use the green one. This is substrate going down like this, and the product P going up like this, where this value here, which will never be reached, is the ratio of P by S, P equilibrium by S equilibrium, right? Which is K equilibrium. So the substrate will fall and the P will rise. Remember, the total sum of them has to be constant. S naught is equal to P upon S. Sorry, P plus S. P plus S, what am I doing? And so the substrate will fall in the. So this is how the profile in the PFR will look like. And in the CSTR, this is, I mean, I'm giving you the answer now because you're taking too much time. In the CSTR, this is S naught. This is S and P. S and P coming out, S out and P out. Unfortunately, the concentration in the reactor is also S out and P out, isn't it? And so the velocity of the reaction V here, the V, which is equal to Vf minus Vr, will actually be for these concentrations, which is of course very, very low. So in a CSTR, you will need a very large CSTR indeed to get conversions where S out and P out are close to S equilibrium and P equilibrium respectively, because then the reaction rate is so damn slow. So you will need a very large CSTR. But here, at least for this zone, for this zone, for this zone, reactions are fast. At this point only, reactions have slowed down significantly. And so increasing the length of this PFR is not going to help anymore, or reducing the time is not going to help anymore. So when you are asking for 55%, glucose to go down from 100 millimolar, at infinite length it will go to 50 millimolar. And it will go down very quickly from 100 to 80, and then much more slowly from 100 to 60, and very, very slowly to 55, and almost infinite time to reach 50. So obviously a PFR is preferable because it is integrated over time, the concentrations are changing. So all industrial transformations, because the rates are faster at S naught and decline as they reach close to equilibrium, would prefer a PFR rather than a CSTR where the concentrations are equal to the outlet all the time. Is this point clear? Hello?
Yes.
Yes, sir.
And obviously you now realize that any PFR with larger and larger, smaller and smaller Peclet numbers, and hence larger and larger axial dispersions, are not to be desired. Does that make sense? Because on the one hand, this means that the residence time distribution, this is the mean, and if all of them reside for this time, because these ones which reside for, they're coming out early, so they reside for less time will get less conversion, but those ones which come out late and reside for much longer times are not going to increase. So this zone of the higher conversion zone, which has resided for equal time, will not compensate for this zone which has resided for less time and has had lesser conversion, because the increase in conversion is not proportional to time. You do it for less time, you will get less conversion here. This part will get more highly converted because it has got more time. But remember that more time, the conversion, so this section, I mean, I'm putting very crude numbers, this is 55, this will become 56 at the most, but this will become 50. So the average of 56 and 50 will be 53 instead of 55, which you would have otherwise got if you had no Peclet number. I mean, I'm sorry, very high Peclet number. I'm not doing the actual integration. I'm sort of trying to put some numbers because I've got used to MSc students not understanding algebra at all. Do you understand this argument? So low Peclet numbers are going to reduce your conversion efficiency. So you don't want axial mixing in the PFR. You want it as a perfect ideal PFR. Is this argument clear?
Yes, sir.
Okay, thank you. So let us stop here. So this is the kind of problems you need to go back and practice. You have just chapters 1, 2, and 3 of the enzyme kinetics, but they don't. The enzyme kinetics book don't contain engineering. The reaction engineering textbooks contain only reaction engineering. You have to combine the two and sort of think of what kind of conversions you would get with simple monod kinetics and with reversible monod kinetics in a CSTR, in a PFR, and how you would generate the data points, and of course the elasticities. So I hope this is it, and the exam on Friday, Wednesday will contain this basic enzyme kinetics and the recombinant protein production expression systems. Okay, and I'm assuming that you know your reaction engineering, you know your PFR and CSTR equations. That is an assumption. Any questions? Thank you.
Thank you, sir.
Thank you.
Thank you, sir.